Hello everyone, and welcome to Psych 301 Lab for this week, where we're going to be reviewing correlation in this first video, and then there'll be a second video posted probably in tandem with this one that's going to review simple regression as well. You should watch this one first and then proceed to watching the regression review, similar to how lecture was presented. So let's go ahead and just jump right in. So we're going to be talking about the correlation between two variables today. And when we talk about correlation, we're kind of referencing this broader underlying concept of what I'm going to call a statistical relationship. Now, when we're talking about a statistical relationship, the easiest way to describe this is just to think of it as a question, or I guess it's a proposition. How changes in one variable are reflected or expressed as changes in another variable. So we'll go through several examples throughout this review, but for example, there's some common variables we might think of as being associated with each other or linked in some way. So you might say things like, the more anxiety I have, the less well-being I might have, or the more exercise I get, the better I feel, or things to that effect. So really, we want to quantify this information in some way and see how, in this aggregate sense, how changes in one variable are reflected as changes in another variable. Now, at this stage, it's really tempting to make some sort of causal statement about this. Well, if my anxiety goes up, that's going to cause my well-being to go down. And while that may seem kind of sensible in a common sense kind of way, right at the outset, we want to make sure that we're a little bit careful with how we conceptualize and describe correlation or statistical relationships. In other words, we want to be clear that these things are not causal. At least they're not causal without further investigation, and that investigation would come in the form of experimental design, where you run some sort of true experiment with random selection and allocation and control groups and all that jazz. For correlation, we're really just seeing how on average things change together, and actually we'll see how that concept of the average bears out and how we actually calculate this correlation. But for now, let's talk about the facets of a statistical relationship, and there's three in particular that we're going to focus on. So when we have this statistical relationship, or I'll just say stat rel for short, when we have the statistical relationship, it actually has kind of three broad facets we have to consider. Two of these things are described by Dr. Siegel in his lecture explicitly, and I believe he probably makes reference to the other one, but it's also kind of taken as an assumption of calculating a correlation in general that this is the case. So I might be doing a little bit of extra work here, but this is just how I like to present this concept. And that particular concept is that of form. So for this statistical relationship, it's going to have three broad facets that I'm going to touch on. It's going to talk about the form of a statistical relationship. We're going to talk about the strength of a statistical relationship. And finally, we're going to talk about the direction of a statistical relationship. So these three broad categories are important to us. However, we want to give special attention to this idea of form, at least at the very beginning of our thinking about a statistical relationship. And that's because form should come before all else. And by that I mean that calculations we choose to assess strength, as in the strength of a statistical relationship, depend on form. This will be made clear as we review this, but this is an important idea. The idea that how we choose to calculate the strength of a relationship, of which our standard idea of a correlation coefficient is such a calculation, we choose that based on the form of that statistical relationship in the first place. In other words, some things, like our regular correlation coefficient, otherwise known as Pearson's R, or the Pearson product moment correlation, that depends on the relationship between the two variables having a particular form. So let's get a little bit more of a closer look at what we mean by form. And I'll first start by giving it kind of just a roundabout definition here. So when we talk about form, what we're doing is we're describing what I'm just going to say as shape of the relationship. And the easiest way to conceptualize this is to do the following. Imagine we were to draw a line of best fit, or if you like, a regression line or a summary line through our statistical relationship. In other words, on a scatter plot. For those of you who might not know this term or might not be familiar with what a scatter plot is, I'll show you that in a minute. But in general, we want to ask the following question. If we were to draw a line of best fit through our scatter plot, what shape would that line be? What shape would that line be? So let's go ahead and examine this a little bit more closely. Let's first talk about just what a scatter plot is for those of you who might not remember. So a scatter plot takes a y and an x-axis, whatever those two variables might be, and it plots the intersection of these values where each scatter point represents a person. So let's say that participant 1 scored a little bit lower on X and a little bit lower on Y. That would be, that would be participant 1, where they have their intersection of their X score and their Y score represented here. So we're going to do this for the entire sample of people, and we might get a scatter plot that looks something like this. You might describe this as like a scatter cloud or something to that effect. And we can imagine how this scatter cloud can take on different shapes depending on how this data, or depending on how the relationship between these two variables actually is. So let me go ahead and put a few examples on here for you to describe what we mean by form and how it can differ. So imagine we had something like, let me do it this way. Imagine we had something like this. each of these is going to have x and y axes, x and y to each stand for a different variable. And we can even do a few more here. Okay, so you can imagine a situation in which we have our scatter plot looking something like this. And here, if we were to draw a line of best fit through this, that line would be best represented as just a straight line. In other words, this straight line here provides us with a good representation or summary of kind of the form of this set of scatter points, or this data cloud, if you like. You can see that if I were to kind of circle it here, it has a clear trajectory, and that trajectory can be described as kind of like a straight path forward. In a way, this line, and we'll talk about this more when we talk about regression in particular, this line here kind of is like my average of the scatter plot, if that makes sense by analogy. It's kind of like, a summary statistic in a way, in this kind of broad way of thinking about it. It's not actually a summary statistic, but we can kind of think of it as such. It summarizes the scatter plot here. So let's think about what would happen if we had some different forms, or our scatter plots took on some different shapes. We could have something like this. We might describe this as curvilinear, and it's a situation in which putting a straight line through these scatter points might be a bit deceptive. If we were to do so, we're obviously leaving a lot of space here where that line is not passing through the overall shape of that scatter plot. In other words, this might not be a linear relationship between these two variables. We might describe this as curvilinear, or if we want to be more broad, nonlinear. And it might better be represented by something like, in this case, a U or a parabola shape, where you can imagine having a set of scatter points that look something like this. Maybe this is better summarized with a S-curve as opposed to some sort of straight line. And then we have the instance in which the relationship between the two variables x and y is actually not very apparent. In other words, there's really no relationship at all. For example, if we have something like this, that is not really indicative of a strong statistical relationship in some way. And in fact, there's no kind of systematic way or aggregate way in which we can see how changes in x result in positive or negative changes in y in any sense. It's kind of just random. Likewise, we could have a relationship as such, and it would be really tempting to look at a relationship like this and think, well, that might be a linear relationship. Wouldn't it make sense to put a straight line right through those dots? Well, this in fact is also not a statistical relationship. And the reason being is because as we see changes in x, as x increases, y remains constant through that whole procedure. And so if we define a statistical relationship as how changes in one variable are expressed as changes in another, or how two variables vary together or covary together, then this kind of does not reflect that definition very well. So what we've covered here then is, in broad terms, three types of forms. We have linear form, which is just this first panel here. These two reflect what we might describe as nonlinear. In particular, we have a curvilinear shape and an S-curve here. And then these two at the bottom, these two can be described as no relationship. And in particular, this one here, we might call a flat line non-relationship. In other words, it's not just that the two variables, as we saw in this first panel, don't change in any conceivable direction necessarily. It's that changes in one variable, here x, don't result in any changes in y. In other words, those things might be completely unrelated from one another. All right, so what does all this form talk matter to us? Well, it turns out that what we're going to be concerned about in most of the analyses we encounter throughout our social science or psychology lives, and in particular for this class that we're teaching about, are going to be of this linear form. So this linear form is important to us because in order for the calculations of our, say, correlation coefficient that we're going to talk about in a moment, we're going to have to be confident that our relationship between the two variables of interest, whatever they are, is a linear one in terms of its form. Otherwise, the calculation of the correlation coefficient we use here, if we were to do that on, say, something nonlinear, that might be a misleading estimate of the strength of those two relationships. Some other type of coefficient would need to be calculated besides the one we're going to learn today. So, when we're talking about our statistical relationship, we have these three components as we mentioned. We have form, strength, and direction, and we need to make sure that that form is linear before we proceed to doing anything else. A linear relationship is going to look something like this, where there's kind of a scatter plot or a data cloud here that kind of trends in some sort of linear direction, whether it be from this end to this end or this end to that end. And we need to make sure that that linear form is maintained before we proceed to calculating a measure of strength. So, broadly speaking, our interest is in linear relationships. And that's where we get terms like linear regression and so on. So once we have confirmation that the relationship between our two variables is linear, we can proceed to talking about the strength of the relationship between two variables. So let's dive into that now. Let's talk about strength. When we talk about the strength of the relationship between two variables, we're really referencing the degree to which two variables vary or change together. And again, this is not a causal statement. This is more a statement to reflect an aggregate idea of, generally speaking, if this variable tends to go up, the other one tends to go up too. Or generally speaking, if this variable tends to go up, the other tends to go down as well. But sometimes those can be a little bit more direct than in other times. So some variables can be more strongly correlated than others. The way that we're going to talk about calculating strength is going to be the same as we saw in lecture. So that is going to be what I'm going to refer to as the covariance approach or the covariance method. And to do that, I'd like us to quickly recall a couple things that we've talked about both in Psych 210 and here in 301 before. So first, I want you all to remember that we have the variance and standard deviation for a single variable. and that is how a single variable varies amongst itself. So we might have our sample variance here, how a single variable varies amongst itself. And when we say that, what we're really saying is from its sample mean. And remember what this variance term really is, right? A variance, as we calculated here, is each score for one variable minus that one variable's mean squared divided by n minus 1. Now the n minus 1 denominator is a slight modification. That minus 1 helps us in other problems. But in general, we know that this variance is an average of things. We know that anytime we take the sum of some things and divide by the number of things that there are, in this case it's a slight modification with the minus 1, but anytime we take the sum of something and divide by the number of things that there are, we're calculating an average. And in this case, we're taking the average of the sum of squared deviations from the mean, and that's what our sample variance is. So we can describe this as the average of the squared deviations from the mean. All right, and we learned about this procedure. We didn't describe it as such, but we learned about this kind of procedure of describing variability for a single variable. And that procedure had two broad steps. We talked about one, calculating a variance, in this case, our sample variance. And in a second step, we talked about standardizing a variance, which in our case, to standardize a variance, are what you might call a standardizing step, was to take the square root of that variance and obtain a standard deviation. A standard deviation. So remember that our variance is going to be given to us in raw score units. And depending on our variable, the variance has the chance to be wildly different from variable to variable. The simple way of putting this is that it's just really hard to interpret a variance term in light of other things, or to compare variance terms. So we learned about how we can transform this to a standard deviation, and how we can use standard deviation units, for example, in our Z metric and elsewhere, to make things a little bit more compatible in comparison, or just to kind of understand things on a similar scale. A lot of times when we talked about this in Z scores or in other contexts, we talked about it in terms of transformation to some common language. Like if I think of temperature in Fahrenheit degrees and you think of temperature in Celsius degrees, maybe we should both convert to Kelvin and talk in that language together. So it's really helpful for us to standardize things. And we learn that standardizing comes in this two-step procedure where we first calculate the variance and then we got to standardize that variance in some way. Well, the way that we talk about a correlation, or the way that we're going to calculate a correlation, is going to follow this very same two-step procedure where we're going to calculate a variance term and then we're going to standardize it. So let's look into that quickly. I'll say that calculating the strength of a linear relationship follows the variance standard deviation procedure. But for how two variables vary together. And the way that we're going to do this is we're going to first calculate a variance term, but this is a special variance term referred to as the covariance. Co, because we have two variables. We can think of that covariance as being, we can represent that covariance with the following notation. Sometimes you see it referred to as cov xy. Other times you see it referred to as a variance xy to show that it's a covariance. I'm going to follow this notation here today. So we have covariance, we calculate this, and in the second step, we standardize that covariance. So we calculate a variance and standardize it in the same way we saw on the previous slide. And when we calculate this standardized covariance, that's going to be referred to as a specific statistic or a specific term, and that is R. Sometimes you see RXY, depending on the notation. But this R here, this is our correlation coefficient. And this follows some other names too. Sometimes you see it referred to simply as Pearson's R, or you might hear it referred to as the PPMC for Pearson product moment correlation, or sometimes you see them referred to as zero order correlations as well. Broadly speaking, whenever we use the term correlation without any other descriptions or context, it's kind of by default assumed that we're talking about this particular statistic here. So, in other words, a correlation coefficient is a standardized covariance, and a covariance is just a metric of how two variables vary together, in the same way as a sample variance is a metric of how one variable varies amongst itself or varies relative to its mean. So I think the easiest way to break this down or present it further is to kind of draw a comparison between the one variable and the two variable situation. So let's go ahead and do that. Let's say we have our one variable context on the left-hand pane. So I'll say one variable here, and our two variable context over here on the right. Excuse me, my spelling and writing on this thing. I'm still a bit uncomfortable with it. Anyways, so we have our one variable and two variable context. Let's compare how these two things work together, how they contrast. So in the one variable context, we saw that we have a sample variance, that to calculate this sample variance, we take the sum of each squared deviation from the mean, divide by n minus 1, and there's our sample variance. Well, one thing I want to draw your attention to is how this variance equation can actually be expanded a little bit to reflect something else. So when we say how one variable varies amongst itself, notice that if I were to expand this numerator here, it looks something very similar to what our covariance is going to look like. So I'll get to that in just a second. It might be a better idea for me to first show you the calculation for a covariance. So for a covariance, to calculate this, we're going to use the following equation. We're going to take the sum of each of the first variable's deviation from its mean times the second variable's deviation from its mean. This is sometimes referred to as the sum of cross products, or simply SP. and we're going to divide that by n minus 1. So in the numerator of our sample variance, we have the sum of squares, and then in the denominator, we have degrees of freedom. Here, we have the sum of cross products in the numerator for covariance, and likewise, the degrees of freedom in the denominator. So, at first glance, these things look similar, but a little bit different. Notice for the covariance situation, we don't have any squaring going on, but we do recognize that we have one variable represented here and a second variable represented here. So this is really going to show us the variability between these two things, or how they change together. It's not quite the same when we're talking about a one variable situation, because we have the square going on. But as I alluded to a moment ago, we can expand this, and that really shows how these two variance terms are very similar. So if I expand this numerator, watch what happens. Our variance equation then becomes the sum of each score on x minus the mean times each score on x minus the mean, right? Anytime we square something, we just multiply it by itself. So if I kind of undo the squaring or expand out and write it in long form, it's just one thing times itself, that times that. And again, divided by n minus 1. So whereas for the covariance, we saw that we have two variables represented in that numerator, x and y. In the one variable situation, we just have that same variable represented twice, x and x. So in terms of just our concept here, a covariance is really just an extension of our understanding of a variance. It's the average of how two variables vary together. Whereas in our one sample situation or one variable situation, a variance, a sample variance, is the average of how one variable varies amongst itself or with relation to its mean. So that would be step one of our procedure, would be to just calculate our covariance here. Well, then we're going to have our next step where we're going to standardize these things. And to standardize these things, we know for the one variable situation, it's pretty straightforward and simple. We take that variance, we take its square root, and that gets us what we need, our standard deviation. And truth is, we have a different standardizing process for our covariance, but it's actually not that complicated of a step. Each of these variables, this x and y variables, are going to have their own sample means, they're going to have their own sample variances, and therefore they're going to have their own sample standard deviations. And so to consider both and to standardize this thing as one term, we might look at it like this. Remember, this is the calculation for our regular correlation. Our correlation is going to be equal to that covariance in the numerator divided by the product of each variable's standard deviation. So we'll have a standard deviation for x, so we'll put a subscript x there, and a standard deviation for y, so we'll put a subscript y there. In other words, we're going to take the product of each variable's sample standard deviation. So x times y, and we already saw above here in the first step how x and y are represented in that covariance together too. So these two things are going to produce for us a Pearson's R, which is cool. It's a sample statistic that's actually already standardized just like a standard deviation. So Pearson's R, or just a regular correlation, is that standardized relationship between two variables. So Next, I'm going to turn to the direction of our correlation. And this doesn't refer to the strength, but it refers more to how the two variables are related in terms of whether one goes up or down on average relative to the other. So let's go to direction then. Facet number 3. So for direction, I think it's easier for me to just draw them out than try to define it. But we could have a positive or negative direction. And maybe what I'll say here is that, that the positive or negative signs of our correlation coefficient tell us the direction. So we could have positive or negative correlations. For a positive correlation, if we were to represent this on a scatter plot, it would look something like this. We have our x and y axes, and that relationship would start somewhere on the lower left and trend upwards to the upper right or middle right. In other words, it would just have a direction that kind of goes from left to right upwards. So that relationship here is a really strong relationship that's linear. Goes up in that direction, and that line's not perfect, but whatever. Goes up in that direction. The idea here is as x increases, on average, y increases also. Forgive me, I ran out of room here. Let me redo that. Y increases also. So as x increases, y increases also. So some examples for this might be as exercise increases, let's say average or someone's duration of exercise, their well-being might increase as well. The more exercise people get on average, the better they feel on average. We also have negative direction. That scatter plot would look something like this. I'm going to make it a little bit smaller so I can avoid that watermark there. We have our x and y axes. And here we would have a relationship that starts higher on the left side than it does the right. So I'll make something that looks a little bit like this. And the trend would be overall decreasing as we summarize that relationship there. And so the interpretation here is as x increases, y actually decreases. And you can see that as we get farther to the right on that x-axis, as x increases, our y values go down, which is why they meet at this point down here. So, for some context, you might think that if x is, again, exercise, y might be something like blood pressure. The more exercise people get on average, the lower their blood pressure gets. So negative doesn't necessarily mean bad or negative connotation, and it doesn't even mean weaker in terms of the strength of the correlation. It just means that the relationship is different than what we'd expect from a positive relationship. That is, the two variables just change in different ways. So I want to make that clear. Direction does not reflect strength. strength. A correlation of negative 0.5 is just as strong as a correlation of positive 0.5. The negative and the positive signs here just reflect that those that the two variables in those relationship change in different ways, but they are changing in equally strong ways. So for a positive relationship, we would expect our correlation coefficient to be greater than 0 because it's going to be a positive value. For a negative relationship, we expect that correlation coefficient to be less than 0 because it's going to take on that negative sign, right? And for no relationship, if our variables are not related, we would expect that correlation coefficient to equal 0. So, if we were to have a perfect positive relationship, a perfect negative relationship, and a no relationship visualization here, they would look something like this. A perfect positive relationship would have our x and y, and we'd have points that perfectly line up in a perfectly straight line. So it wouldn't even be as if we had some sort of scatter plot. There'd really be no deviation from this line. So excuse me, my drawing's not perfect, but I hope you get the gist. A perfect negative relationship would have that same thing, but just going in the downward trajectory where we have all these points here that fall on essentially a straight line. There's no real deviation from that line. I don't mean that to look exactly like a triangle, so let me get rid of that there. And same up here. Do a little bit of cleaning. Right? A perfect no relationship would look something like that flat line, where no change in y occurs as a result of changes in x. Or it might be some really good version of this, where there's no real direction in terms of the line at all. It's just sporadic and, in a sense, random. So that's the gist of the three main facets of a statistical relation: form, strength. Let me just write this out actually. Statistical relationship, form, strength, and direction. We talked about form and said that in order for us to calculate strength in the way that we observed with our Pearson product moment correlation, we need to make sure that the form of that relationship is linear. And when we say linear, we just mean that the scatter plot follows a shape that could be best described or summarized with the straight line going through it. We talked about strength in terms of it following that standardized variance procedure, where instead of calculating a variance like we would for a one variable situation or a sample variance, we calculate what's called the covariance. And then we standardize that covariance just a little bit differently than we would a regular variance. Instead of taking its square root, we divide that covariance by the product of each variable's standard deviations. And then we talked about direction and how the direction of that relationship does not reflect its strength, even though there's positive and negative signs involved, but rather the direction of a relationship just tells us how the variables change together, not how strongly they do. So whether on average, if one variable increases, the other variable also increases or decreases. So don't let the loaded terminology of positive and negative kind of throw you off in direction. So that's the general conceptual idea behind our correlation coefficient. And let me also, while I'm at it, just throw a few more things here for you. Let's talk quickly about just kind of like a potpourri, I guess, some features of a correlation. Our population notation for a correlation is going to be this Greek fancy P symbol, which is the Greek letter rho. So just like we have mu for a population mean or sigma for a standard deviation, rho is going to be our population parameter relative to a correlation. We've already talked about the sample notation as being reflected as R for our Pearson product moment correlation. And when we run a hypothesis test to see whether we have a significant correlation or not, we're going to have some null and alternative hypotheses that essentially look like this. And it's a pretty easy concept to get through, I think. We want to test whether our population parameter rho is equal to 0 or whether rho is not equal to 0. And this assumes a two-tailed test. But in other words, when we run a hypothesis test for a correlation, really we're just asking, is our correlation significantly different from 0 in some way? And remember, 0 refers to no relationship. So, is our correlation coefficient that we obtain in our sample significantly different than the situation in which we'd have no statistical relationship between two variables? And what's cool about R, in fact, our correlation coefficient, is that because R is already standardized, it's actually our test statistic. So if I go and I calculate a Pearson's product moment correlation of, I don't know, R equals 0.68, all I have to do is compare that 0.68 to whatever my critical value is. And then that's how I can determine my test. If this 0.68 is greater than or more extreme than my critical value, then I have a significant correlation. We don't have to calculate a separate test statistic or go through some of the same hoops that we otherwise would for things like a Z, T, or an F test. Last thing I want to mention is that our Pearson product moment correlation is kind of like our sample mean. So like our sample mean, R is influenced by outliers. R is influenced by outliers. So you can think of it this way in terms of like the regression line or the line of best fit. Imagine we have this relationship here. And to represent or summarize that relationship, we can put a line of best fit through it as such. Now imagine we had the exact same relationship here. It's not going to look the exact same in my drawing, but just pretend it is. Imagine we had the exact same relationship here, but we also had this big glaring outlier down here. Well, what that's going to do is that's going to actually drag our line of best fit down a bit with it. And the way that we can visually interpret strength is that we don't want a lot of deviation from our lines to the scatter points. So the more deviation we have on average, the lower our correlation is going to be. So when we have something like this, drawing our line down, not only is it drawing our line away from these other scatter points and causing that deviation to be larger, but it's also a large deviation itself. So we'll talk about that more in regression, and that'll make a little bit more sense when we talk about this regression line in particular. But here, just know that like our sample mean, R is also a statistic that is influenced negatively by outliers, such that the outlier is going to actually drive the correlation closer to zero. It'll either get more positive if it's a negative correlation or more negative if it's a positive correlation. So that wraps up our Khan Academy style review of correlation here. Again, this is meant to supplement my overhead presentation that I would otherwise do, but I hope that's helpful. As always, email me with questions about correlations if you have them, and I encourage you to continue on and look at the review for linear regression that's going to be posted to accompany this as well. So thank you, and I'll see you on the next one.